Good afternoon, guys. It is a blisteringly hot summer afternoon, but that ain't gonna stop us doing some maths. Now, we're gonna go through three questions: bronze, silver, and gold. These are basically just questions depending on how confident you feel and how able you are at maths. Just choose the one you feel comfortable at and give it a go. Just don't look at the answers. I will go through them in a second. But just pause the video, give yourself some time, because I don't want to rob you of the opportunity to grow your brain through problem solving and through just trying to do it yourself, okay? So let's look at the questions. Alright, so starting with the bronze one. So we want to find out how many even numbers there are from 1 to 100. Now, if you just look at the notes I'm going to write, I'm going to show you a way to visualize this, okay? A lot of you might do this immediately. But this is the way that I would visualize it, okay? So we can think of the numbers, just writing a list of them, right? From 1 to 100. Now, we're interested in how many even numbers there are amongst these numbers. Now, let's just recap what even numbers are. So even numbers are numbers that have 2 as a factor. Basically, you can split them in half and you're going to get a whole number. So examples are like 10. 10 divided by 2 is 5. So obviously that's a whole number. So we say 10 is even. We'd say 11 isn't even because that would be 5.5 when we split 11 into 2 parts. So, it's quite a simple idea about what even numbers are. So we can see clearly that actually 1 isn't even, right? 2 does not go into 1. But 2 is even, right? 2 times 1 is 2. Yeah, that'll do it. 2's even. 3 is not even because 2 doesn't go into 3 a whole number of times, right? You can only fit 1 2 in with a remainder of 1. Now, obviously 4 is even, and if you look at the pattern, the numbers are going to be 2, 4, 6, 8, blah, 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 going up to 100. So basically we're looking at the 2 times table. So we're thinking how many numbers out of the 2 times table do we have in this list of numbers. Now, this is the way that I would personally divide it. There are a lot of different routes to do this. Imagine if you... Actually, no, let me not draw that again. Let me go back to this. So imagine just pairing up all those numbers all the way up to 100. Now, clearly, can you see that at the beginning of each pair is an odd number and the end of each pair is an even number? So because 100 is even, we can imagine that actually that's going to end up being at the end of a group, so we can have groups like that. Now, if you think about it, play with it in your head, but we have now actually, if we do this for all the numbers from 1 to 100, sorting them into pairs, every one of them is covered, it's in their own group. Now, let's think about how many groups there are, okay? How many groups are there that we've made? Well, I know how many numbers there are from 1 to 100, right? It's 100. I think that's pretty clear. So there are 100 numbers if you count from 1, 2, 3, 4, all the way to 100. So if you think about it, we can kind of form 2 different groups, okay? We're going to, basically you can think of them as these boxes. I'm going to put each number from 1 to 100 into these boxes. Now, I'm going to put the first number from each bag, from each pair. I'm going to put the first one into this box here, right? And you can imagine I'm going to keep going. And the biggest one is actually going to be 99 because actually these are the odd numbers. And the second one, I'm going to put all of these, the second numbers, the second number in each bag, I'm going to put that into this group, okay? So, yeah, actually, you can see that they're going to be an equal number of things in each box, right? Because each pair we split it, so one of these goes there, one of these goes there, etc. These are going to be the same size, but actually these contain all the numbers from 1 to 100, so we've split 100 into 2 equal groups. The thing about division is that captures that idea. We split 100 into 2 groups, that's going to be 50, so 50 in each group, but these are your even numbers, right? These are all of the even numbers. So we have 50 even numbers, and that's your answer for the first question. The answer should be 50. Okay, second one is a bit harder. So let's just scratch that off. So we're looking at the growth of like a tree or something like that. Okay, so let's just look at the different years we have. We have year 1, year 2, year 3, and as long as some hooligan doesn't come along and rip the tree down, this is going to go on pretty much indefinitely. Okay, so let's just draw a picture, okay? Really recommend it whenever you have a problem that you want clarity on in maths. Draw a picture, it will visualize things, make it a bit clearer for you to see what's going on. So at the end of year 1, we've got a lovely little sprout, okay? 1 leaf. Now, if you look at the question, it says after the year after, at the end of the second year, right, at the end of year 2, this stem has branched into 2 branches, okay? So this little leaf died away in the winter, a bud came, in the spring the following year, year 2, it split into two of them, okay? And towards the end of that year, we've got 2 lovely leaves. Okay, so this pattern continues. It says that basically at the end of each successive year, the leaf from the previous year has formed 2 new branches, and each of those branches has a leaf at the end, okay? So clearly, because these are my 2 leaves the previous year, and these are going to give us 2 more leaves, okay? So you can imagine that I'm going to do this for a long time. Now let's think about actually the number of leaves, okay? So with 1 leaf here, 2 leaves here, 4 leaves here. Now you can think of a pattern. Okay, we're timesing by 2, and that's going to be your key to working out the answer without you having to just, wear away the skin in your hand by writing out from like year 1 to, how many is it again? We're going to the 14th year eventually, so we want to save ourselves some time. So, and you might know that the reason why we times by 2 is because if you think about it, however many leaves there were in the previous season, so in this case 1 leaf, each of those leaves is going to birth 2 more. So if 1 was the number of leaves we have, we'll have 1 lot of 2 that come from this one. Similarly, 2 leaves here, so we have 2 nodes here basically, and each of those previous leaves have given rise to 2 more. So we have 2 lots of 2. And similarly, keep going. Okay, similarly we keep going. These 4 leaves are here, although they're not leaves anymore, obviously. They've given birth to 2. So now we have 4 lots of 2. 4 groups of 2. So we say obviously that's 8, but actually, you know what? It's 4 groups of 2, okay? i.e. 8. We've times 4 by 2 to get the next one. Okay, now let's just dive in with the answer. We're pretty much there now. So after the 8th year, so if you think about it, we want to go all the way to, let's just scratch that out. Eventually we're going to get to year 8, okay? So imagine we're going from year 4 to year 8. We're going to have to jump quite a few years in between that, obviously. So how many times do we jump from year 1 all the way to year 8? Well, if you think about it, it's going to be 7. Be careful, it's not 8. If you just count, there's 1 year from year 1 to year 2. So if the question was asking you how many leaves there are at the end of year 2, we would have only times by 1 2, not 2 2s. Similarly, for year 3, we've times by 2 times. And for year 4, we've times by 1 2 3 times. So clearly the pattern is we timesing by whatever the number of years it is, it's going to be that minus 1. So we want to do, we started with 1 to get from year 1 to year 8, we're timesing by 2 7 times, okay? We're doing that 7 times. So clearly the number of leaves at year 8 is going to be 1 times 2 times 2, and I'm doing that 7 times. Now there's a way to write that in maths. Let's brush up on notation. If we do, obviously 1 times this lot is, we can just ignore the 1, right? 1 times anything is itself, so we can ignore the 1. So we have 2 to the power of 7. So the way we write that is like this. That's saying that we have 7 2's that are multiplying together, okay? Not 2 times 7, it's 2 times 2 times 2, blah, blah, 7 times, okay? So that's actually the answer. Now, in maths, honestly, it's better to get a general result even after doing just one question like this. So it's useful knowing how many leaves there are at the 8th year, but how can we extend this? What is the pattern? So for example, let's look at the 14th year, okay? how many leaves are there after 14 years? So basically at the 14th year, you think about it, we'll get the same answer. We're going to do 2 times 2 times 2, blah, blah. And how many times are we doing that? We're doing it, as we said, it's always one less than the year we're on. So it's going to be 13 times. Now, if you want to do this on a calculator, you probably, after school maths, have probably burnt your calculators, for most of you. I know what you kids are like. But this is how you do it. So this symbol here, okay, it's x to the power or something. So basically you can fill out the number here and the number here to whatever you want. So let's put 2 here. Oh gosh, no. 13 here and 2 here. So this is going to save you some time because you could, like, you know, I don't know, you could just like do 2 times 2 times 2 on your calculator 13 times. But actually, way easier to do the power thing. So the answer is going to be 8192. And actually, silly me, I didn't even fill out the answer that we wanted in the first place. At the 8th year, it was 2 to the power 7. We're not going to be a plonker and do 2 times 2 times 2 times 2 times 2 times 2. Wait, 1, 2, 3, 4, 5, 6 times 2. We're not going to do that, okay? 128. Better to do that little thing. We're going to do 2 to the power 7, and lo and behold, 128, okay? So that is the answer to that one. Okay, and if I want to, now I know that, you know, algebra, not many of you like that name. I think you can grow to like that name, just give it a chance. Let's do some algebra. So the reason why this is powerful is saying, okay, at the nth year, whatever n is, let's just pretend it's a number, right? It could be, in this case, n could be 8, n could be 14. Whatever number you're looking at, whatever year you're looking at, the rule is you're going to have this many leaves. 2 to the power of n minus 1. That n minus 1 is going to be the number we're going to write as the index, as the power, okay? And that's what's going to get you an answer. So that's that one. Let's move on to the goal question. All right, let's go for gold. So there is going to... knock that over. That's not good. Okay, let's think about this question, okay? So I feel like, I think I would have done this, especially with... to start off getting an idea of how this question works. I would have started just to literally think about the sequence from 1 to 99. And I would just think to myself, okay, how many 9s am I going to expect? I could maybe list them out. So I'm expecting all the numbers that have the digit 9 in them are going to be 9, 19, 29, blah, blah, blah. Be careful. 99 actually contributes 2 to the overall number of 9s that appear in this list, right? It's not just 1 9 here, it's 2 9s. Blah, blah, blah. You can even get a number like 991, blah, blah, blah. And actually, when you get to 999, that's the biggest number, obviously, that contains 9s. So we've got this. So you can either count all those, and that's fine. You're probably going to be there for a bit of a while. But I've actually asked you later on, what about the list from 1 to shock horror 9999? Okay, that is a big number. If I wanted to extend this indefinitely and ask you for even more, even larger numbers, then clearly we're going to have to come up with a better way of doing it than just counting manually how many 9s there are. So I want to show you a really awesome trick, okay? And this is basically how the trick goes. Instead of thinking about the sequence 1 to 999, I'm sure you'll agree, our answer is not going to change if we just add 0 at the beginning, if we start counting from 0 instead of counting from 9. So we're looking at these sequences. Let's start with this sequence here, okay? Let me just write it out again. So how many 9s appear in this sequence? That's what we want to work out. We're looking at digits, right? We're counting how many digits there are. And we have some digits are 1-digit numbers, like these ones, and towards the end, they actually become 3-digit numbers, right? So a vast range of them. But actually, I'm going to do a little trick. I'm going to write each number as a 3-digit number. This is totally legal. Okay, I am allowed to write 0, 1, 2, and blah, blah, blah. I'm allowed to write every number here as a 3-digit number, even though you don't normally write 1 like this, for example, or 2 like that, okay? The reason being is obviously place value. That's just saying we have 0 hundreds, 0 tens, and 1 1, which is the same as 1, okay? We're allowed to do this. Now, imagine you do that for all the numbers from 0 to 999. Don't call that number, by the way. It won't end well for you unless you really need it, okay? So basically, yeah, let's think about what's actually going on. We want to count how many digits are 9s. But let's think about, first of all, how many digits are there in total? Imagine if we counted how many digits there are, whether or not they're 0s, 1s, 2s, 3s, all the way up to 9s. How many are there in total from here to here? Well, clearly, there are 3 in each, for each number, right? We're counting 3 digits in each number. And how many of those numbers are there? Be careful, it's not 999 of them. If I cover this one up, there would be 999 numbers. It's going from 1 to 1999. It's not that. It's going to be one more because we're adding this one, right? So that's going to be, it's 1,000. Okay, so 3,000 digits in total. Now listen, some of these digits are going to be zeros, some are going to be 1s, 2s, 9s, okay? We want to work out how many 9s there are, but this is the trick, and I'll tell you before I prove it. The idea is that they're going to be an equal number of zeros, an equal number of 1s, an equal number of all the way up to 9s, okay? They're going to get an equal share. Now you can think about that yourself. I'll go through it. And so think about it. We've shared our 3,000 digits that we have amongst these numbers. We've shared them in between the digits 0, 1, and 9 because they occur equally often. So how many have I split 3,000 into? There are actually 10 groups. Be careful again, it's not 9 groups. If it was 1 to 9, it would be 9 of them. But we also have another one, so 10. So basically, how much 9 receives is going to be 3,000 split into 10 equal groups. That's going to give you 300. That is quite big, isn't it, actually? You would have been there for a long time if you accounted manually. This is why it's so powerful to deal with. What do you even call it? Patterns in maths. I don't even know how to say that, but you know what I mean. The way that we've approached this problem is more valuable than just manual counting, okay? A computer can do that, and you're more than a computer. So this one gets 300, this one gets 300, blah, 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 and we find our answer. Now, I needed to justify something to you. I needed to explain more clearly how do I know that each of them get an equal slice of the digits, right? Why do they all get 300? Why doesn't 0 get maybe 400, and then 1 get 200 and blah blah blah? Why do I know they get equal amount? So the way that I'm going to do this, it is going to require a bit more thought. Okay, so let's get started. So this is the idea, guys, and this is a really neat trick. Okay, so imagine that I've got all my numbers from 0 to 999. Actually, I'm going to make it a bit bigger just so that I really reinforce this this idea. So let me do many more examples. Maybe also a number that doesn't include any 0s or 9s. Let's say like 439, like, you know, whatever, and all the way up to 999. Okay, so this is the idea, and this is a really amazing trick. So I'm going to create a rule where I'm going to make another sequence below it. Each number is going to get mapped, it's going to get sent to another 3-digit number, okay? So it's going to get sent to any other number that's on here, and this is the rule. I'm basically going to swap 0s and 9s around. If it's any other number, like 1, 2, 3, all the way up to 8, I'm just going to send it to 1, to itself. So the 3s don't change, nothing else changes, only 0s and 9s switch. Now, let's think about where 000 will be sent to. So that 0 is a 0, obviously, sorry, it becomes a 9. So this one will become 999. This one will get sent to 991, 992, okay, all the way up to, okay, this one actually would just stay the same, right? There are no 0s, there are no 9s, okay? This one will get sent to 430 because 9 gets switched with 0. And 999 gets sent to 000. Now, the question is, do these each get sent to a different number? Okay, basically, have we just reshuffled this sequence? Okay, do we have each one going to a different number, and so all of the numbers from 0 to 999 are they all captured in this sequence, or there's some missing? Do we have maybe 2 different ones going to the same one? These are questions we need to ask. Okay, so let me talk about the first thing, about whether or not 2 different numbers actually go to the same number. So I shouldn't have scribbled there. I'm going to use this space now. Okay, this is the idea. Imagine whatever numbers we got here underneath them, let's say that I do the rule again. Okay, I do the rule again. Can you see that this number is going to go to 0, 0, 0? This number's so silly. I shouldn't have done this. Scribbled here. This one's going to go to 0, 0, 1. This one's going to go to 0, 0, 2. This one's going to go to 1, 2, 3. Okay, we're just doing the same rule again, right? The same rule again. Now, you might notice that actually we end up at the same place where we started. And that's because if you think about it, the rule was you just, whenever you see a 0 or a 9, you swap it with the other one, right? Zeros get swapped with 9s, 9 gets swapped with zeros. Obviously, if you do that twice, so let's say you start out with a 0 somewhere, that 0 gets swapped to a 9, and then if you do that rule again, that 9 gets swapped back to a 0. And likewise, if you started with a 9, that gets swapped to a 0, then to a 9 again. So clearly we end up where we started. Now that's actually why we never could have got two different numbers somewhere mapping to the same 3-digit number. The reason is, let's say that they went to the same one. Okay, let's say instead of writing these two numbers going to the same one, actually if I had written them just as I did up here, we would have had obviously the arrows going down. This one would have been mapped to, let's say, x, whatever this is. They both would have been mapped to x. Now, if you think about it, because these are the same, I'm sure you'll agree, if we apply the rule to the same number, you're going to get the same. You're going to get the same outcome, because this rule applied to 002 is always going to give you 992. It's not going to give you, if 002 happens, let's say 002 happened twice along here, it's not going to give two different numbers. It's going to give the same number, because what you put into this rule determines exactly what comes out. So clearly, with these two, although they give you the same, they should actually give you the same output for this one. But we've just said that if you apply this rule twice, you're going to get these two being the same, the endpoints being the same. So these have to be the same, and these have to be the same. But because this number has to be y, because it has to be the same as this, and this number has to be y, because it's the same as this, lo and behold, these have to be equal to, these are also both y, which kind of contradicts what we assumed about these being two different numbers in this sequence. So clearly we can't have this situation because we've got a contradiction. If it was true that they both map to the same number, then we would have got a contradiction. These wouldn't have turned out to be different in the first place. Okay, so each different numbers here, each number in the sequence maps to a different 3-digit number. But think about it, all the 3-digit numbers that could end up on the bottom row, they're all found along this row, because we've done the list of 3-digit numbers, all the possible 3-digit numbers we can, right? So imagine, because they all go to a different one, this let me do it again, right? This sequence gets mapped to different numbers, okay? If these all have to go to another 3-digit number, let's say, so actually this one goes all the way to that, 001 will go to 9, oh gosh, that's not there, is it? It's bad. Right, 991. This one will go somewhere else. So they all have to map back to this. And because each of them have to map to a different number along the 3-digit numbers, as we just said, they get a different outcome every time you apply the rule and you switch those digits. Can you see we're gonna pair all of them together? Like, you know, each of them has to go back to at least to exactly one of these numbers along here. And clearly, if you have the same list of numbers, okay, and you're going back to the same list of numbers, where each of them go to a different pair, let's say, you know, you have things like that, then there has to be the same number of these as this, obviously, and all of these have to have someone mapping to them. Otherwise, you're going to get overlap. You're going to get two of them going to the same place, which can't happen. They have to go to a different place. Think about it. If there were actually 3 numbers instead, let's just say x, 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 whatever, they have to map to different things. You're going to get 3 different numbers. If it was 4 of them, voilà. If there are 4 of them, and each of them maps to a different, let's say y at a different number, these are going to have to map to 4 different numbers. So basically, and the reason why this helps us is that imagine, so since that all these numbers here essentially occur along this line but just reshuffled, okay, these are all the 3-digit numbers, these are all the 3-digit numbers. What I'm going to do is I'm going to count how many zeros there are in this sequence, but I'm going to count how many 9s there are in this sequence. Now looking at the way that these are mapped, okay, if I count how many zeros there are, can you see that these two have, if I count how many zeros there are, this is going to contribute 3, but I'm counting the 9s in this line, so this is going to contribute 3 as well. So when I'm adding up my zeros, the number of zeros, these contribute the same as how many 9s there are. So imagine I'm counting how many zeros there are in these numbers. There are 2 zeros here, but look, there are 2 9s here. There are 2 zeros here, there are 2 9s here. This is going to be a pattern for all of the numbers. There are 0 zeros here, there are 0 9s here. Can you see the pattern? 0 zeros here, 0 9s here. 0 zeros here, 0 9s here. But so if I count out how many zeros I have, I'm going to add the same. I'm going to get the same sum in the end as how many 9s there are, because each time I do it, count how many zeros and 9s there are, they contribute the same amount each time. That means that there are the same number of zeros as there are 9s, and so we've proved it. So truly there are the same number of zeros and 9s, and that's what we wanted to show. So going back to it, we've solved it. There are, I think it was 300. Yeah, there are 300 of each of the digits. So we've actually proved a bit more than what we wanted to prove. But let's go back to the question about 999. Okay, 999, 9999. So all the numbers from 0 all the way up to 9999. Okay, we want to know how many 9s there are. I asked you that question later on in the gold question. Now to do this trick again, we can extend it, right? There are 4 digits in each, so the number of digits in total from 0 to 99999 is going to be 4 digits in each, and there are 10,000 numbers here, so that's going to give me 40,000 digits in total. Now these are going to be shared by a similar argument in between the zeros, the 1s, and the 9s, okay? All the way up to 9. So each of these get an equal chunk of 40,000 digits, right? So 9 appears in equal amount of times as 0 appears in all of these numbers, going from 0 to 99999. So to work out how much each of them get, well, that's clearly going to be just 40,000 shared equally amongst, this is the same symbol as dividing, by the way, dividing by 10 symbols here, that's going to give me 4,000. So actually, it appears 4,000 times. Okay, thank you for listening. Those are the questions, bronze, silver and gold. I hope you enjoyed it. Let me know if there's anything you want me to quiz you on in the future. Just DM me. I'd love to hear what you want me to talk about, basically. So just feel free to suggest something. But yeah, I encourage you to do these just daily exercises if you can, because it doesn't have to be these ones. It could be anything. But just doing maths every day does keep your brain kind of ticking over in a nice way. It keeps you always going through like fresh challenges, and you need challenge to stretch your brain, right? That's always the case. You need to, it's always been the case that if you want to like learn maths, you don't just read textbooks, you have to do the questions associated with it, because your brain responds to challenge basically, and it grows according to that. So thank you for listening, and I hope to see you next time. Okay, thank you, bye.